this 4-day Julia course. Let me start with introduction and the materials on the course. So first of all, we would like to say great thank you for Professor Alan Edelman for inviting us over to have this lecture and to present it. The course will take over 4 days. So here is the detailed schedule of the course. You can find it on the GitHub website. I understand everybody has the link to the website. There are also installation instructions that I will also mention in a minute, and we'll have a look at those installation instructions. Last but not least, this course for the participants from the MIT will be graded. So there will be homework. The homework assignment will be given during the last lecture. So the homework assignment will be given during the last day. There will be one for the participants at the MIT. There will be 1 week to do the homework assignment. And the homework assignment, you will be kindly just asked to send me to my email address. So in this way, we can check them. Also, in the meantime, once you get the homework assignment, if you find out you have any problems or something is not clear and so on, you are also invited not to hesitate to ask the question. So the homework assignment will be for the MIT students only who do this course for credit. Okay, so I think this is the time to get the things rolling. I'm going to start with, of course, Julia introduction. So just the last thing to note: this is not an advanced course. This is an introductory course. So we'll be starting totally from the beginning. We are not assuming that you have any kind of Julia experience previously, that this is your first time with that this is your first meeting with Julia, and this is the first time you are seeing and working with this beautiful programming language. Okay, so let me get the things rolling. So the first thing you need to do, you need to install Julia. Those latest versions always updated, so it's as of today, and of this course it's 1.8.5. So this is the latest Julia version that you can download from the website. We will be working with Jupyter notebooks. So this is how we are going to work throughout the course. And you can find the detailed installation instructions. So if some of you didn't install the Julia yet, please do it in the time I'm going to talk about how to run, how to set up and Julia and so on. This looks like a perfect time if somebody of you forgot to install Julia or didn't do it yet. Please do it in the time when I'm going to talk about the introduction. Also, we have friends who will be teaching you on other days or other parts of the courses. They are monitoring this online. So should you have any questions regarding Julia installation, if something doesn't work for you or you have some problems, do not hesitate to ask this on chat. So here in the materials for the day one, you can find the detailed installation instructions, how to forward. So basically, you check out this GitHub project and run few comments that are presented. Run the few comments that are presented on the screen. So should you have any problems with installations, don't hesitate to write in the chat, and we'll be trying to help you with that. Okay, so this is as far as the installation process goes. I will be perhaps switching between the slides and consoles and the course materials. So hence, let me start with the first thing about Julia is the Julia command line. We'll be working normally with Jupyter Notebook, so the Julia command line will not appear for too long. but this is the first thing I wanted to show you to tell you that Julia has a beautiful wrap. So Julia has a beautiful command line system. So you can see it. Yeah, it the default mode is basically the place where you can do your programming like this, but also it has other modes which are also available at Jupyter Notebook. So one mode for the Julia command run is the package installation mode. So Julia has a built-in package manager, and when I press square bracket, what you have here on the slide, when I press the square bracket, I'm moving to the package management mode, and I can, for example, see the status of the I can see the status of the installed Julia packages. I can add a new package and perform the other actions with Julia installation. I go back from the mode pressing backspace. Then I have the command line mode when I can execute any command line like ls for list files in folder. Then I have and some plugins can provide other modes for the Julia command line, but this is worth noting that there is more than one. So you can use this to install Julia packages. I assume that you have followed the installation instructions that you have been given during the course, and that all the packages all packages have been installed. Now, the next thing we are going to use Jupyter Notebook. And in order to be able to use Jupyter Notebook, what do you need to do? You need to, again, in the command line. So I'm using here Windows, but it honestly doesn't matter whether you use Ubuntu or something else. Mm, I need to you need to go to the folder where you have downloaded the materials. This folder to start as you have performed the installation, and here you are loading the package. And here you are, so it's again in course materials, you are activating the current project. So we are doing the command pkg activate the current project, which is dot. Okay, so it sees all the packages. It sees all the packages that you have installed if you follow the installation instructions. So there is a package configuration folder. So we all have exactly the same packages. We all have exactly the same package versions and so on. We're working with Julia. And then you type using iJulia, which iJulia is Jupyter Notebook for Julia. And then you press did started, so I will not press enter here, that you write something like notebook directory equals current. This is going to book, and this is the beginning of your work, Julia. Once you start the Jupyter notebook, the browser is going to be launched, and and then it's going you it's going to take to the folders, and from the available folders you are going to choose the day one, which is the first step. So I have already it open, but some people that name Jupyter, people are familiar with the name, but don't realize that the JU is recorded with PY our language. So the first letters come, or Julius come first. So it didn't get recorded online, it just stands for Julia. So place when you it means you yes, this is indeed mentioning. Fighter node. One then you start the Fighter notebook, you are going to see screen with a lot of messages like that. So do not close when Jupyter notebook is running. be needed. Jupyter not where console the Jupyter is running, so the notebook the web browser is going to get started, and this is when you work with Julia. Oh, this is the and now we presenting the main language. So this is a language that is at exponential rate. Probably its selling idea is what Python like C, run like C. What is behind it? So the idea is that to have a programming language, it's as easy to write as Python or MATLAB. So people in my data science, data analytics, people use very often Python prototype, but then they discover the code runs too slow, and they need to rewrite it. C. So this was the idea behind Julia development, to build a tool that you don't need to first write in Python and then read it with C, because Python is too slow. So we have language that talks about Python and runs not by it combines to assembly, which we have a look on. Combines to GPU, will not GPU. You can run, you can write a Julia function and then compile it on GPU. And hey, in this Julia function can write on a GPU accelerator without changing the actual code. Another thing, this thing will be showing on Friday. There are many questions. Why do we have another language for data science? And the problem it solves, I've just mentioned. So this is the two-language problem of data science. So we previously we were really using Python, but Python was too slow. And then we needed to rewrite code with C. Or as you know, most of Python libraries are also written in C. So if you want to debug Python in NumPy, then what about? Then you are only left into having a look at C code, which is not so convenient. Moving on to that, here we have a table. What are the ways to achieve high performance with various programming languages? And again, the point is that if we have an R-based stack, then we need to use C. If we use Python and want to GPU computing, we very often need to use for hot code, you need to program in C or Numba and so on. And the Julia is the only programming language that you can cover all parts of the programming stack in Julia, either when gluing the application, when running that code that requires high performance, or when running the GPU code. Another alternative maybe is MATLAB, but MATLAB is very expensive. So I have heard of computing center that needed to spend up millions for license update, which is not always so friendly. And I think as of today, for scientific computing, Julia is it's starting to win over MATLAB. And so what is nice about Julia? So these are performance benchmarks. And what do we have here? So we have here a set of tests, so various computational tests. On the x-axis, we have programming languages, so we have several programming languages, and the y-axis is log scale. This is the performance. So we have log scale performance of those languages, and you can basically divide languages into those that have high speed computations and then that have lower speed of computations. So why do we have so many languages? So one motivation could be, this is another picture, that we have language that we can have a look at how fast the language run. So on the y-axis this time we have again execution speed. Note this is log scale. Okay, so this is not linear scale, this is log scale. So on the y-axis we have log scale execution speed, and on the x-axis we have the length of code. And up to Julia was invited up to the point that Julia was developed, you had a terrible alternative. Either you had to write a code that is easy to write, it's comfortable to write, but takes very long to run, or you could write a code that runs very quickly, but this is difficult to write. So on the x-axis, we have the length of the code. So how much programming you need to do to achieve an effort. This was designed for a specific use case of numerical simulation and so on. But basically, you can get such results. Basically, you can get such results throughout many projects. Okay, so you are seeing how what are the motivations beside the language. So these are the four main pillars of the language. This is performance, scalability, modern design of the language, and also the MIT license. Okay, so these are the key features of the language. Okay, so before I move forward, some of those slides will be then interwoven with what we have Jupyter Notebook. So before I move forward, let's go now to Jupyter Notebook. So this looks like it's a good time. This looks like it's a good time to go with Jupyter Notebook. So here we are running Julia in a web browser, which is probably the nicest way to do it for educational purposes or for data exploration. So the first comment we usually run, we check what Julia version we have installed and whether the Julia is installed. This is version info comment. So Jupyter Notebook, if some of you have not used Jupyter Notebook, this is organized into cells. So each cell is containing a piece of code, and this piece of code is getting executed whenever you press Ctrl Enter. So pressing Ctrl Enter causes this piece of code to be executed. So this is it. So you are seeing what Julia version is installed in my machine, and this is the first comment. The next comment, which might be very useful, sometimes I want to find out what is the folder when I am running my computations for. So this time I'm using Microsoft Windows. So this is some Windows folder wherever I have put this Jupyter Notebook into. Another basic command is the command for the package manager. If you remember the previous slides, at the beginning of this presentation, I've been telling you that Julia has many modes. Okay, so that the command line has many modes. So there is standard mode, but there's also package manager, help mode, or interacting with the command line. So this is also supported here. So ST is it's a shortcut for status. And the square bracket, this is a Julia command line comment. It's not a Julia comment, actually. This works like a magic comment in Python. So it says, hey, now I do not want to issue Julia comment, but Julia package manager comment. And this is the comment about the status. So when I press Ctrl Enter, what am I going to see is the status of installed Julia packages. And so these are all Julia packages that I have in my installation. And assuming that you have followed the instructions given in the course materials, you should be seeing a very, very similar list, as the contents of this list is controlled by the project.tom file that runs a configuration for Julia installation. So this is the status, and this is how you can see it. Similarly, you can list the contents of the folder by using command line comments. So ls -li, this is a command. This is a command line. This is a command line comment, and what we are going to see here, this is a list of files in the folder. So again, this is another thing about the Julia command line, that if you want to switch to something else, you can do it very easily. Okay, so let us start looking at some properties of the language. We start by defining a very simple function that adds to numbers. So here is the syntax of a function. So you can see that blocks in the Julia language are controlled by the end statement, contrary to other programming. So in some other programming languages, you might have curly braces. In Python, you might have a colon and then those cuts of commas. So here the decision was made to use and the blend of code. If you have one-liner functions, you can just skip the function keyword and use the kind of definition that looks quite like mathematics. So I'm defining here exactly. I'm defining here. I'm defining here exactly the same function. Now I can call that function, of course, and this is nothing surprising. What is interesting is the Julia compiler system, and now we are going to slightly comment onto this Julia compiler system. So Julia feels like Python, so you can work almost interactively. But what is interesting, it has a multi-stage compiling system. So how does it work? So you start with source code. So you have a source code, then you have tokenization. So this is parsing of source code. Then there is something that is called abstract syntax tree. Any Julia code can be represented in Julia data structures. It's extremely interesting. So we might mention it somewhere sometime later, but any piece of code in Julia is also represented in the middle of compiling process, is also represented in the Julia itself. And then what's happening, you have several stages of compilation. So you have first lowering, so you have first lowering the code, then you have, for the lowered code, you have the typing information. Then the code gets to a set of C compiler systems, which is called low-level virtual machine. And if you are running, most of you, I see here, have laptops, MacBook laptops in this classroom. So most of code on your MacBook is also compiled with this compiler. So this is very good and very stable compiler system. So low-level virtual machine is a set of compiled compiler system. Then it's being then LLVM is performing several steps of optimization. Then we have intermediate code, and in the end we have a native code. Now, if we define any functions, actually we can have a peak in this compiling process. So if I have my function, I'm using here a function with some given parameters. So Julia knows which version of function to use. Julia is using multiple dispatch for typing. So the types of parameters are defining which version of code is going to use. And I can see this code at various stages of compilation. So this is multi-stage of compilation, but Julia has a set of macros that allow me to give a peek on what is going on. So this is the first stage of compilation. So this code has been processed into some code info block. Then in the next stage of compilation, it already knows that since both arguments were integers, so it's known that the result is also integer. This is a performance issue. It's very good to write code in such a way that Julia compiler can understand what is going to be output type of the results. It's important for when writing complex code, it's important for efficiency. Okay, then this code goes to low-level virtual machine, and here is the code translated into a set of instructions for the low-level virtual machine. So this is the code. This is the code translated for level of instructions for low-level virtual machine, and then is the assembly. Of course, you do not need, normally when you use Julia, you do not need to look at something like that, okay? So you just run the code. The code gets compiled, so you can pick into each stage of the compiling process. So you have really a multi-stage compiler process, and you have really a multi-stage compiler process, and you can pick into any step within, you can really pick into any step within this process. One thing also worth noting is that Julia is using multiple dispatch. So the version of this code, so the version of the final compiled code will be very different depending on what data types you have. So if I have here two integer numbers, I have one version of assembly code. But supposing if, for an example, I have here one integer and one floating point number, I'm going to a different version of assembly code. So Julia is going specialized for the types of parameters. Also from the types of parameters, Julia can guess what is the output type of the function. So if we call such functions type stable, when looking at the input types, we can infer the output type of the function. So depending on what types are got, and this goes through entire process of compilation, processing, and so on, depending on what input types we'll have a specific machine code. Now we are going to move on to various elements of the various elements of the language. Julia is using quite sophisticated uh, Julia is using a quite sophisticated type hierarchy that even for numbers, we have abstract types, then we have abstract number, abstract real, abstract integer, and so on. We'll be looking at those types in a minute, and maybe let's have a look at some. I will now walk through various functions of the language. So the first thing are the vectors. So a vector is defined as similar to Python. So we use square brackets to define a vector, comma to separate vector elements, and we end up with a vector for elements. So here we have a special type vector. So actually, vector is a shorthand name for one-dimensional array. And then we have the elements of the vector we have elements of the vector 1 2 3 4. Okay, so this is how it looks like. Now you need to note that everything in Julia is typed. So we have type of the results, but we have also the type of container elements. So these are parametric type. So int64 is the type for the elements of vector. This is similar to Python. If some of you are coming from Python, in Python we have dtype. In NumPy, we have dtype when any Python container can have types, when a Python container can have types for its element. Now, similarly to what we have, in Python, we can use comprehension syntax. So, for an example, we can make elements for 3x. Now, this is interesting that if it's obvious, like in mathematics, you do not need to use multiplication sign in Julia. So basically, when you have a number and multiple by a variable, you do not put it needs to star here. So this is going to create us a numbers from 1 to 9. So these are the ranges. This would be quite similar to what you have in Python, a range of 1 to 10. Okay, so in Python, you would have a range 1 to 10. Note that unlike in Python, in Julia, the ranges are inclusive. So the last element of range is within the range. So this is similar. This is similar to many other languages. One more thing, so at least the second thing, in Julia, vectors and arrays use one-based indexing. So this is quite similar to mathematics and not similar to languages such as Python, C++, and others, but similar to R or MATLAB. So what does it mean? If I want from this vector, if I want to have the elements from, if I type 1 to 4, I'm actually getting, it was V3. If I'm getting from these elements from first to fourth, I'm actually typing 1 to 4. So it's not like, it's not like some of those programming languages when you are enumerating elements that. Elementary linear algebra. Yeah, maybe elementary algebra. I agree. Yes. Said that we do zero based like Python and C, or one based like Julia and R, and
you know, more support over lesser things. Why don't we just split the difference and start at 0.5?
Oh, this is a good idea. So for those from who are listening for online, there was a joke that you can either start from 0 or from 1, and there is discussion, and the compromise, I understand the great compromise would be to start numbering from 0.5. It sounds like reasonable solution. Yeah, it would work. Yeah, you can start from any number. Yeah, Julia has libraries that you can start indexing from any number. You are flexible here. Okay. Also, Julia has several types of syntactic sugar you are going to see in many locations. So suppose you want to use some kind of indexing, kind of like in LaTeX for symbols, you can do that. So if you want to have this small number 4, so this lower index, you can do it quite like lower index with in LaTeX, but use just slash. So use slash to try to enter something like you would be entering in LaTeX, and you can write, for example, slash alpha and press tab, and then you are getting alpha here. But you can also write slash underscore 4 and press tab, then yeah, you have lower index 4. It's using Unicode to represent that, so so not everything is possible, but probably you can very easily make your Julia code to look like the code in your mathematics handbook. Okay, so this is how it looks like. Then you have square root of x1, and again, this is another nice syntactic sugar. You can type square root like sqrt, like you would be doing in again in LaTeX, and it works even without parentheses x1 for x1 in this range, or even for in, I could type here slash in and press tab, and this is also going to work. Okay, so this is something very nice because you can keep your Julia code very similar to your textbook, to the code in your mathematics textbook, and this makes code much more readable. So you can see at this time we have a vector of float 64. So if we ask about types of this vector, so here's the previous v3. So maybe I'm going to change it for v4 this time. Doesn't matter so much. So you can see that the type of v4 is a vector of float 64, where actually in Julia, a vector is an alias type for one-dimensional array of float types. So hey, here it is. So we have those elements, and then we have a separate function to check what are the types of elements in a vector. So if you are going to check what is the element of type, I'll type v4, and you can see it's float 64. Okay, so this is how it looks like. When you want to make an empty list, you specify the type of elements, and this creates an empty vector. Okay, so this is a vector when you do not have any elements. Of course, you could append an element, say append b by 5, and then b is one element with 5. Okay, but this is how you can create an empty vector. What you really do not want to do, but you do not want to create an empty vector like this one. So this one can have any object. And if you remember what I told you about the Julia compiler, that it can very cleverly adapt to whatever is there and infer the data types and nicely compile it. If you are going to create a vector like this one, then the Julia compiler will not know about the type, which is very bad. There are two problems. One, each value on this so if you have a vector like this one, it can be directly mapped into memory, because then each piece of the data is an int64 value, so it takes 8 bytes in the memory, and it can be continuously layout in the memory. So this is easy. But if you do something like this, then each value needs to be boxed. Okay, because you do not know whether it's when it's integer, float, string, or elephant. Okay, you do not know what's inside. So you need to do value boxing, which is very computationally expensive, and Julia will not be able to generate efficient code. So why this is quite common pattern to make an empty list, say in Python, you never want to do it in Julia. Now, type can be values can be more complicated. So, for example, you can create complex numbers. So here I'm creating a complex number with real part 1 and imaginary part 4. But if I look at the type of the C, you can actually see that this is complex number in int parameter space. So Julia has this option that any type of anything can be parameterized. Okay, and this is also for complex numbers. So you can parameterize the types. You can parameterize types for such complex numbers. We actually might want to see how this data is being stored internally by Julia, and there is a special command named dump. And this is also quite useful when you are learning the language and you are seeing something and you are wondering what is inside and so on. So it shows you the raw data of the object. Sometimes this information is going to be quite complicated if you have like a hash table, hash map. These are complex types, and what you are going to see inside is not so nicely readable. But if you have just complex number, you can actually see how the complex number is stored, that it contains a real and imaginary part, and together it takes 16 bytes in computer memory. Okay, this type of complex number. Of course, you might want to store complex number rather on the space of real numbers rather than integer numbers. Maybe integer number-based complex system does not make sense, but Julia makes it possible to do so due to its very flexible typing mechanism. But if you want rather to have complex number over real numbers, over float numbers, you can also do it. You can say something like this, or I could simply use real parameters here. I can check what is the type of this, and I'm seeing type of this is complex floating point 64, and this is how it works. Now, this typing system is something very flexible. For example, Julia is supporting rational numbers. Okay, so I could say something like x equals 1/2 plus 1/4, and then I have 3/4. Okay, and I could check that type of x is of course a rational number. So this is a rational number defined over a space of int 64 numbers. Okay, so the both value are int 64s in this rational number. And for example, I could have a complex number system. So suppose I want to do exact computations over complex numbers, and I'm not happy with this float 32 or float 64 values due to a computational inaccuracy. Then why not? You can define a special type of complex numbers over a space of rational numbers, and maybe these rational numbers are defined over the space of int 128. So integer numbers, but defined in 128 bits. So what it means, you get flexibility with the language, that if you have defined something like a complex number system, okay, and you have all the mathematics to perform various calculations over the complex number systems, they are defined in a kind of abstract sense over any number system. Okay, and you can use them to start that way. You could think of mathematics about floats, but you could totally change the number space, and everything you have implemented for the processing complex numbers, it will just work naturally. So this is a great example how the typing system and the multiple dispatch that is implemented in Julia works in a very flexible in a very flexible way. So here, what I'm doing here, I'm defining a complex number over a set of rational numbers. Okay, so this is what we have. So now we quickly look at data types. So basically, we define strings with apostrophes. So you can use parse function to convert between data types. For each data type, you have a special function 1 and 0. This is sometimes those functions are actually useful when you want to write code that is kind of elastic to type. So this is 0 in float 64, and this is unsigned int defined on 32 bytes, and so on. Here's a set of basic function for data conversion. So character types, similarly to C or Java, these are defined with a single apostrophe. So you have a single apostrophe to define the character types, or just a single character. You can convert the data. You can convert the data between the types. So you have 2.0, and hey, here you are doing the conversion. Of course, it's not possible to do conversion such as this, because this will yield an exact error, because this is 1.3, so it cannot be converted into int. You need to do rounding first. The same about string. So you could convert a single character. So you could take a single character from the string, but not the entire string. You can of course convert integer to float. You have a specific type Boolean, okay, for Boolean values, again, like in any other programming language. So you have 0 and 1. 1 is true, 0 is false. Then you have card types to represent characters. So this takes an integer and converts it to char. Then you can have any value from any numbering system and see what is the 0 in this numbering system, or the type, and see what is the type, and so on. So here we are using a special decorator, which is called show macro. It's not the maybe Python would be called decorator. Here it's macro. Macros are special structures that change how the code operates. Okay, and macros are quite interesting because they kick in the Julia compiling process. So macros are interfering with compiler process to change the behavior of the code. And here we use those macros to show what is the code and what is the result. So you can see very nicely we are seeing the results of all those functions. So this add show is causing that the code is going to be displayed together with the result of evaluating this code. Okay, is this clear so far? So everybody here in the classroom, you want to comment something or ask? Okay. Then Julia has plenty of types, as you have noted. So maybe now this would be good time to mention the type system. So in Julia, this is for numbers, but you will find a similar structure in other places of Julian ecosystem. So here just the numbers, but wherever you look, you are going to find something like this. So you have abstract types that define the core of the type structure. So you have like abstract number, abstract real number, abstract integer, and maybe abstract sign integer, and then you have concrete types, like integer defined on 8 bits, 16 bits, integer defined on 128 bits. Actually, there are Julia libraries that allow you to natively define bigger integers. So you can have in Julia, say, integer defined on 1024 bits. Yes?
Yes, so this flexibility, but why do we need it? Because if I, for example, use R, I don't have to think about all those different types of integers, for example.
Okay, so the question was from the classroom, do we need this flexibility? Because it allows us to strictly define the types. So then the compiler can exactly know what is the type of argument and how am I going to lay out the memory. So then in the end, I end up with continuous memory blocks that can be quickly accessed, and I end up in efficient code. On the other hand, for example, in Python, we have an integer value that can be of any size. But then operations on integers, if you do not know how big is integer, then if you have an array of such integers, you do not know how big the array is going to be. So on one hand, this is of course a kind of burden because you have types for every size of the data. But there's also another thing. So sometimes you know that you are doing operations of small pieces of data. Then why to keep all those bytes? Okay, so if I know that this data I'm doing maybe some ASCII processing and doing some integers, maybe I know that's in 16. Why would I need a bigger type? Okay, so it works. Also, you need to have a fixed size of the data, so you know so you can efficiently align this in memory. And also you can make good use of these small pieces of data because they will just compute more efficiently. So you want to add something?
So it might come handy if someone wants to do, for example, GPU computing, right?
Yes. So this is another thing that on GPU you have on GPU you will be not using 64 bits types. You want on GPU you can use you want to use 16 or 32 bits because this is what is probably supported by your GPU accelerator, and this is already part of the language, so you do not need to develop a specific new language for GPU computing. But it turns out that you can write Julia code, maybe select smaller types like 32 bits for your or for higher performance 16 bits. So you select the smaller types, but then any your mathematical code that was right or working on CPU can immediately work on GPU, which is really great. You do not have to reprogram everything. You do not have to reprogram everything to go from CPU to GPU. Okay, so these are the types. Now, with some parts, I will be going slightly quicker. So we have tuples. So tuples have fixed size, and they work just like tuples in Python. I'm assuming that you probably might have some familiarity with Python or the programming languages. So tuples are quite like vectors, but they are immutable. So you cannot change content of a tuple. Yeah.
There is a question from chat. How are irrational numbers represented?
Okay, this is very good question. So rational or irrational?
Irrational. Like for example, pi.
Okay, so we have a special number pi, and the type of pi is irrational. So we have a specific data type for irrational. Okay, and what we can do when we print this pi, it depends. We can change between. We can no. How do I? We can change between. We can change between the precision. So there are specific types to represent those rational values. And when we do computing on them, we can set the precision. So we have set precision. Yep.
So you are doing is I will just add one more comment for the person who asked. So as you can see, if you check the type of pi is irrational, but with parameter pi. So actually, every such irrational number has its individual type, and this way, Julia knows that we represent pi with undefined precision, so let's say infinite precision. And what Przemysław wants to show is that only when you try evaluating pi, you actually materialize it to some other type, depending on what kind of or what level of precision you need. But before you materialize pi, it's like an abstract concept of a pi that is irrational with infinite precision. But once you start computing on it, you get this pi evaluated to the precision limit.
Okay, so hope it was heard. This is abstract concept, and in the meantime, I've just shown that whenever you see, then it gets materialized. And actually, we have a similar materialization concept in other areas such as arrays and so on. So Julia in many areas supports unmaterialized objects, and you can do operations on such. So maybe we do another demo of arrays as well. So here we can change that, and you can change the precision and see what is happening. So these are the tuples. So tuples are just like vectors, but immutable. So you cannot change the value. So maybe we, so I think it's quite self-explanatory. So I will not be talking too much on that. Then we have arrays. Then array can be defined as then array can be defined as a set of elements, and basically the basic definition is that you do an array, you provide the type of the elements, then you provide the default value, and you provide the dimensions. You provide the dimensions for the array. Okay, this is how you define arrays, and there are type shortcuts. For example, and so I will be doing again some examples here. So for example, you can define a matrix. So matrix has already a set number of dimensions. So matrix, if I look on, what is matrix, matrix is an alias. Okay, so it's an array of elements of some type T. So everything has an information about the type of elements that has 2 dimensions. Okay, where T, it means that the T can be parameterized. So this is how Julia is writing that T can be parameterized. Okay, so this is technical, but in practice, it's right, our matrix. So then you know that you want to have array of 2 dimensions. Then you provide the information about the elements of the matrix. So here these are int numbers. Then default values, undef is a special keyword. It says, just grab me any piece of my memory. Just grab me any piece of just grab me just you can see here that you have you can see here that you have you can see that you have the matrix. So let's see what's going to happen. So there are already some values here because it took any place of the memory. Okay, I did not define this default value for the matrix. I said it's undef. So whatever the bytes in my system memory are holding, I'm now seeing as part of my matrix. Okay, so this looks like this, that any rubbish that got free just for memory for my needs, now I'm seeing this as the newly created matrix. You can, of course, create a matrix of 0. So this creates a matrix of zeros by dimensions 4 and 5. So this way I'm getting such matrix. You can assign values to matrix just like you would be doing in any programming language. So you have square bracket that defines the dimension. So this is the first dimension, this is the second dimension. The only thing you need to do is that you are doing the one-based numbering. So 1 and 3 means first row and third column. So now I have a matrix of 0 when I have assigned the value for first row and for first row and the third column. We can do array slicing. We can do array slicing. So what is array slicing? When you have array, so when you have a matrix, you can select from the matrix which rows and columns you want. So column stands it's for all. Okay, so I want to have all the rows and the column number 3. So in this way, from this previously created here matrix, I'm getting all the rows and column number 3. You can do reshape of the matrix. So for example, I'm writing here, I want to reshape 3 by 4 of this matrix. Okay, and Julia here is very smart because Julia is very good about non-materializing objects. So you can see what I got here. I didn't get a matrix. I got here something which is called 3 by 4 reshape, and this reshape is somehow defined. So information about this is written in the type of the element. I could actually make this into a matrix using a special command named collect. Then collect, then it gets collected to an actual matrix. But Julia is, like you saw with the number pi, Julia is quite good about working with unmaterialized things. So suppose my matrix was big, like this. I do not have so much memory in my computer to hold 12 billion of elements. Okay, because I would need to have 100 gigabytes of RAM, okay? But since I'm not materializing it, if I make matrix this big, my computer doesn't crash. If I do now collect, I will run out of memory on my Windows machine, okay, immediately. So if I try to materialize such huge monster, of course, it's not possible. But as long as I'm not doing anything complicated with that, Julia will be really efficient about working with unmaterial. So it's working about some abstract concept of matrix. And of course, this huge matrix, I could be trying to ask it about some specific element, and then Julia will give me that specific element. But this matrix can be as big as, and it's actually some limit, so I could probably multiply it by 2 or add some number. It also supports some simple algebra, as long as it could store this outcomes of this algebra in the type information. And also one more thing, you can see that for huge matrices, Julia is also quite smart about the way it's stored. So we are also always seeing the left top corner, right top corner, left bottom, and right bottom corner. Because this is usually how you want to have a look at the data. Usually when you do data analytics, the most interesting things are happening at the beginning or at the end of the data. So whenever somebody is doing it, you know that if something goes wrong, it's always either at the beginning or at the end of the data. So Julia is quite clever here. Later, Bogumi is going to also present data frames, and you will also discover that this is a good way. This is the good way to display it. Okay, this is about matrices. So should you have any comments? I think I've run onto most almost important parts, most all important parts here. Now we are going to have some look on data structures. So Julia is not object-oriented programming language. Julia is using multiple dispatch instead. If you are used to object-oriented programming languages such as say Java, C++, or Python, perhaps, then sometimes you will slightly need to change a way of thinking, but you can define the data structure. So here I have some funny point that this point, so this is a struct. So struct, it stands for structure. Structures, data structures can be either mutable or immutable. If I, by default, if I do nothing like here, the structure is immutable, and making structure immutable, this or immutable changes the way it's stored in memory, and of course access to data that cannot be changed, that were immutable, will be much faster. Okay, so if you know the data do not change, you can get higher efficiency by declaring, hey, this data, this piece of memory is not mutable, it's not going to change during the execution of my program. So here I'm defining the struct, I'm naming the struct. So this is kind of funny point because the first parameter is integer, the second is a floating point number, and there is a meta information which does not have any type information. Basically, this is discouraged. So we do not like in Julia data structures that do not have defined the type. This is actual equivalent to writing something like this is any type. So this could be of any type that has maybe structure, maybe some other data. Whenever you have some data structures that do not specify the data, usually it slightly destroys the efficiency. So in this way we can create a point. So we are creating. So here we are creating the point. So this is a small piece of code. I have created here a point. So this is called this is held as point blah 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 blah. I have here assigned the value of 0 to x. Then I can query the data structure about what do you have inside. Okay, so this is field names. And field names does not work on specific objects, so it does not work on P, so it does not work on object, it works on the type of the object. So you cannot query an object what data it has, you need to find out the type of the object. So you ask about what is the type of the object, and then you get information about field names. This is an equivalent of just asking field names of this type of object, of course. Okay, and it shows, and here for the first time, we are seeing something we are going to see many times, information with colon. So a piece of string with colon is used in Julia to represent symbols. So before I move forward, let's if I write something like dump x, so this is symbol x. Okay, you will be seeing that when working with data frames, when you have columns and you might be using strings or symbols to represent columns, you will also be seeing it some other occasions. So at some places, rather than using strings, you will be once you get to use it, it's kind of more natural because this is a field in a data structure. Okay, so a field into this data structure, it's kind of more natural to represent this as a symbol. But it's quite easy to move between symbols and strings. So this is something also not embarrassing. So let's have a look at this our P object. If I dump it, so you already know the dump command. I'm seeing here the internal data of this object. So you are seeing that this is int64, float 64, and now the type information has been assigned. The type information has been assigned to that specific field. Oh, and here we have this discussion on symbol that I just did. Now, very often when you are defining data structures, you want to have a default values. Okay, so you have defined some kind of data structure, but now say, I want to have some default values, not just any value in this data structure. So how to define default values in a data structure? This is kind of funny because it was not initially a part of the language, but this has been provided via macro system. So I've mentioned you already about this very multi-stage process of compiling Julia code. So actually macros are programs that change the compilation process in the way they can be used to extend the syntax of the language. Okay, so here we will have one example. There is a syntax extension provided by a micro keyword definitions. So it seems, so it tells that I'm going to define a data structure, but this time I want to extend the syntax of the language to be able to assign the default values. So yeah, and I can do it. So if you want to have default values, you need to use a macro like this one, and then we are doing here a structure point to this is the field X and this is the field Y, and they can have default values, and also this extends the syntax for the constructor of this object. So using macro can have many consequences. So here also now, when creating an object, I can also use the keywords when giving. So for example, I want to create object where Y value is the default value. So I can say, hey, I want to create point to, and I'm assigning the value to X. I'm assigning the value to meta, but I'm not assigning the value to Y, and the Y will be used with the default value. Okay, so this syntax, if I didn't use this keyword definitions, this extended syntax with keywords would not be available for me. I would just only say point and then provide parameters for each of the fields that you have within this point. So this is something really nice. I made this structure not mutable. So of course, when I try to set the value to it, I'm not allowed. Okay, so if I type p2.x equals something, then it's going to throw me exception. To not look ugly, I put it into try-catch block. So now you can see how try-catch blocks look like. And they are kind of not surprising. It looks like this in almost every programming language. So you do your try statement, whatever code that might not get executed, and then you have catch and E. We usually use E because it's our EX because it stands for exception. So we have called exception, and the exception contains. So this is again an object of type exception, and this contains information about what went wrong. And of course, what went wrong here is that I tried to mutate an object which is of not immutable type. To show the flexibility of the language, actually, this is one way to provide the information. This is one way to provide the information about the fields. But there is also a package named parameters that does exactly the same and provides the same syntax, but slightly changes how the data structures are displayed. If you note here, code cell or a block of code Julia always yields the result of the last comment. So here I have created the object named P2, and you see this is represented normally displayed on the console as point2, and these are the values of fields. But once I've used another macro that adds exactly the same syntax to the language, but it has different display pattern. For scientific computing, sometimes I find this more useful. It doesn't. You can do mix and match. You can mix it whatever you want in your program. This is mostly for kind of debugging purposes, what you prefer, or matter of your personal taste. So here it changes how the information about this point are being displayed. So sometimes I'm doing some kinds of numerical computing that I want to have, nicely debugged objects and nicely displayed with many fields and so on. So I use this. I use then the second definition. This is quite comfortable. We have many data types. So now we have dictionaries. So the syntax for dictionary is dict. I have one organizational question. We started 5 minutes later, so we also finish 5 minutes later, or we finish on time. Okay, so let's meet 30. Let's finish 35 maybe because we started 5 minutes later. So, and this is a shorter block. So, okay, so we have dictionaries. So dictionaries are again parametric types. So you need to define the type for keys and the type for values. In Python, you have dict, which would actually be like dict any and any. So in Python dictionaries, do not have stored the information about keys and values, and anything can be stored in Python dictionary. In Julia, this would also be valid syntax, but you do not want to do that. In Julia, you want to be type specific. So here you are providing the information about keys and values for this dictionary. And here I'm providing the information about keys and values for this dictionary, and I have constructed, so this constructs an empty dictionary, and here I'm assigning two fields. We could be, of course, doing this with any and any, which I have already said. Now, if you want to generate values of dictionary at the time you are doing it, you can also provide it with as parameters. So one is 5 and two is 4.5. It generates a dictionary, but then it deserves information. What is this animal? So what is this thing 1.5? And if we look at this, so we say type of this element, you can see it's a pair. Okay, so Julia has something which is named a pair of elements. In the pair, you have, of course, first element, and there is a first function, and you have last element, last function, and each element of a pair is again typed. So this is the type of the first element and type of the second element. And those parametric types in Julia are everywhere. So everything in Julia has parametric type. Why? Because compiler needs to be able to generate efficient assembly code. And without knowing the types, you cannot align nicely the data in memory, and your code will not run as fast as when you have the type information. Okay, so we have it here. So we can quickly create a dictionary. So here is the syntax for creating dictionaries: empty dictionary, some dictionary, selecting elements. This is already has key. You have seen. You have standard words like has key to check whether a dictionary has a specific key. So you have this kind of thing of in Perl programming languages. You have keys. So this is all keys. You have values. You have a special command delete that deletes an element in dictionary. Now, this is the first time we are seeing a Julia command with exclamation mark. Exclamation mark is not any special character in Julia unless it's used somewhere in logical expression. When it's like in most programming languages, it's used to denote not. But other than that, in the name of the function, it's not saying any specific, but there is a Julia convention. If Julia function is going to change something that is getting as a parameter, use the exclamation sign in the function name to make code more readable. You will see that really lots. You will see that really lots when working with data frames, when you are going to have those exclamation marks everywhere, okay? Because you will be mutating data, changing data, and so on. So this exclamation mark is not a special character. It's not special piece of information. It's just part of the name of the function, where the function names follows a nice convention. If function is changing its argument, let the user know it does it so they can quickly see it that something is changing. Of course, here it's quite obvious. It's delete. Hey, it must change something of its argument, but it's not always so obvious. And we want to communicate this to the user when designing Julia APIs. So now we have text processing. This is quite easy. You just need to know the operators. So text is anything between apostrophes. Use double apostrophes for text and single apostrophes for a single character. Okay, so not like in Python, it's not like in Python where it doesn't matter when it's single or double. He used double apostrophes for text. Now you have for text concatenation, for joining two texts together, you have the multiplication sign, not plus. but in Julia it's multiplication. And there is great explanation why. We do not have the time to discuss it, maybe during the break. Then for power, we have multiplication of text. You can join also text using the string function. It can take any amount of text and you can also concatenate them. You have functions for occurrence and text processing and searching in text. This is easy. You use slash for character escaping, I guess like almost all programming languages. So this is not surprising. Now, Julia uses very nice thing, which is called text interpolation. And I believe this even deserves its own cell. So what is text interpolation? This is known from languages like Bash or Perl. In Bash or Perl, so if you use Bash, you see text interpolation to write some scripts. Text interpolation is something nice. So this allows you to plant variables or even expressions directly inside the text. It's very comfortable when you are doing logs, printing output to the user, printing some stuff to the data. So you can very clearly mix the text with some values. Of course, if you want to say that something is $3, dollar is a special sign, then you need to escape that sign. Okay, but other than that, you can see that this evaluates to text where this value has been placed. So these variables have been placed inside the text. Very convenient. Allows you to keep the code short. Functions. This is something we have discussed slightly in the beginning in the compiling process. Functions can have the same name with different amount of parameters. And having not too much time, you can also run those examples yourself. But assume I have a function g, and firstly, I'm also this one. I'm having function g, and I'm defining it twice for different types of parameters. So one function g is defined for integer parameters, and the second function g is defined for an integer and Boolean parameter. And when I try to see what is inside, so I will have something, we have some method called methods. So you can see that for the function g, there are two methods. Okay, so each function can have many variants depending on the type of parameters. So this is called multiple dispatch. I can have many functions of the same name, but they just differ by the parameter type. So that information about the type is very important when choosing the right implementation. The information on the type is also not obligatory. So you can have many functions definition. So I could still leave having a function g that takes x and y and just maybe it calculate x minus y. So I can have many types. Then Julia is going to select the function that is the most specific to the situation I'm in. Okay, so it will prefer the functions that have more detailed information about the type. But you can have many functions with different functionality, with different data types. And this is really great because you can very easily add various abstractions, various functionality abstractions within the language. Then this will be quick. These are operators. This is overview language, so sorry for going through everything, but I want to give you overview. Then later you will be doing examples and so on, so it will be more practical. So these are the operators. So what is interesting here to know? This is the OR operator. So this everything is you can chain many comparisons operator. One thing which is very interesting is the dot operator. I think you will see this all really lots of time when using data frames with later examples. But what does it do? So in many cases, you need to write a loop. So you need to go through each element, for example, to compare something, to calculate each value of something. So here we have two horizontal arrays. So these are two matrices. These are two horizontal matrices, the size 1 by 2. And I want to compare each corresponding elements of it. Okay, then instead of writing loop, I'm using a dot. So dot is basically replacing me a loop for a series of operations on corresponding elements. It will be easier to understand when we are going to do practical examples. But this is very nice syntactic thing in the language because very often we have some data structures and then we would normally be writing some very complex loops and iterating over elements. Now, the last two things, so I have 2 minutes, one thing per minute. So there was a question about the number of pi. So we already know it's irrational, so I don't need to talk about it. So here we have very simple code to calculate the value of pi. And we can do this with various precisions. So we have different precisions for floating point operation, float 16, float 64, big float, and so on. But then when we have functions like this, you can calculate the size of pi with, so this is, for example, I'm calculating here the size of pi with precision with 10,000 iterations and big float. And here I have the result and I'm exact up to, I think I already did this big set precision 3000. So I have very good, I have exact computation for pi, for example, for 3000 numbers, I am correct. Okay, so you can manipulate the precision. Also, you could calculate approximation of pi, for example, in other numeric systems, still using the same function because of the multiple dispatch. So suppose I'm still having the same function, but this time I'm calculating approximations of pi as rational numbers. Okay, last but not least, I'm not going to show that anymore because I ran out of time. From Julia, you can call many other programming languages. So here, for example, are examples for calling Python or R if you have R installed on your machines from Julia. And there are many others, so you can call C, Fortran, and many other programming languages, really lots of libraries called Python, and we'll be also using that when plotting, making pictures, and so on. Maybe we'll be using, for example, Python backend for data visualization. Now, what is going to, so now we are going to have like, I think 30 minutes break, but what is going there to be after the break? So here you have in the course materials. So after the break, we have presentation by Bogumił Kamiński on working with tabular data. So there's a great library in Julia named Data Frames, and this is something we are going to discuss after the break.